Hey guys, in the last video we took a look at convolutions. Now we'll take a look at pooling. Pooling itself simply looks at a region in the feature map, then does something with the numeric outputs. In some cases it could take the maximum value from that region. Sometimes it takes an average value. What we have on the screen shows pooling, taking the maximum value. That's called max pooling. Pooling requires a kernel. In this case, we're using a 2x2 kernel. What that means is 2 pixels wide, 2 pixels high will be considered in the output of the convolution. In the example that we have on the screen, you can see the values that we have, and the max value is 3. Of course, what this means is for every 4 values, you're going to end up with 1 value, meaning that you're shrinking the size of the output. Depending on the kind of pooling operation, you could have a pool size, you could have strides like the convolution, you could have padding. So padding could help you maintain an output twice the same size as your input. Various pooling operations have been implemented in TensorFlow as layers, and these correspond to convolution operations, and as a result, we have 2D and 3D versions of whatever pooling operation you have. Both convolutions and pooling tend to be introduced in some research papers. So to get the difference between different types of operations, for instance, the difference between convolution and pointwise competition, you're going to need to read both papers. Same thing applies to pooling if you want to know the difference between average pooling and global average, as well as max pooling. You'll need to read the papers. So let's revisit our code. Again, we look at our model. It's a sequential model. What makes it convolutional is the layers that we add into it. So again, we could see that the first layer that we have is a conv2D. The output will have 32 filters, kernel size 3x3. We have an input shape and an activation. Next, we apply a max pooling 2D and the size 2x2. If you look at the output, we could see that the first layer that we have in our output is a conv2D. It has an output shape of 26 by 26 by 32. You could compare that to our input shape, which is 28 by 28 by 1. And immediately, we could see that we've lost 2 pixels in the width and height of the image. That's because we did not specify padding that would let us maintain the size of the output to be the same as the size of the input. There's also an additional dimension that has been added with the size 32, the dimensionality. So that's reflected in our output shape. We can also see that our parameter size, which is 320, and that's the number of trainable parameters. Now in the output, immediately under the first conv2D, we could see a max pooling 2D. We can also see the output shape. In this case, it's 13 by 13 by 32. There's no trainable parameters in this layer. But what we can infer is that if we divide the width or the height of the output from our conv2D by 2, we will arrive at the output of our max pooling 2D. And that makes sense because our max pooling 2D used the size of 2 by 2. So essentially, the size of the max pooling divides the size of the image in the output, which is our feature map. Now we apply another convolution. Again, our kernel is 3 by 3, and we specify a filter size of 64, which is going to be our output. If we go to our output, that's our model summary now, and we look at the second conv2D layer. What we see is that because we did not specify the same padding, our image has gone down from 13 by 13 to 11 by 11. So again, we've lost 2 pixels. But our filter dimension has gone up from 32 to 64, because that is what we specified in our second conv2D layer. Then we go ahead and apply max pooling again. That divides the size of the output by a value of 2, so we have a 5 by 5. This is a general overview of what pooling is doing. Remember, we said pooling is going to downsample our output. Another way to look at it is essentially like we're zooming out from the image. The image gets smaller, but the size of our filters gets larger depending on whether we want it to get larger. That's convolution and pooling put together. Next video, we're going to revisit dense layers.